Welcome to this lecture on algebra. Today we are going to explore two fascinating types of matrices, unitary and involutory matrices. These mathematical tools are essential for preserving information, and they form the backbone of everything from quantum mechanics to secure digital communication. Let us dive in and see how they work. Now that we know our topic, let us start with unitary matrices. Why do we need them? Imagine holding a physical photograph. You can rotate it or move it, but the people inside do not stretch or shrink. In standard real numbers, orthogonal matrices do this job. But when we step into the world of complex numbers, which include the imaginary unit I, we need a stronger tool. That tool is the unitary matrix. It perfectly preserves the original structure of complex data. To use it, we rely on something called the conjugate transpose, where we swap rows and columns and flip the mathematical sign of every imaginary part. Building on that definition, let us look at the mathematical formula. A unitary matrix is defined by a very elegant equation. UH times U equals I. Conceptually, this means the matrix is its own reverse operation, provided you take the conjugate transpose first. Let us break down the symbols. U is our unitary matrix. UH is its conjugate transpose, named Hermitian after a famous mathematician. Finally, I is the identity matrix, which acts just like the number 1 in matrix algebra. If you increase the dimensions of U, the identity matrix I simply scales up to match, always representing a state of zero distortion. Before we move on, let us see this with a concrete example. We are given a 2 by 2 matrix U containing the imaginary unit I, and we are asked to verify if it is unitary. To do this, we must find its conjugate transpose and multiply it by the original matrix. Our first step is to find the standard transpose by swapping the rows and columns. The top right moves to the bottom left and vice versa. Next, we take the complex conjugate by flipping the sign of every imaginary number. The positive I becomes negative and the negative I becomes positive, giving us our conjugate transpose UH. Continuing with our verification, we now set up the multiplication. We place our conjugate transpose UH and our original matrix U side by side. We multiply the rows of the first matrix by the columns of the second matrix. This step requires careful attention to the negative signs and the imaginary units, so we write out every single multiplication step to avoid careless errors. When we simplify the arithmetic, the cross terms involving 0 completely disappear. This leaves us with zeros in the top right and bottom left positions and the term negative I squared on the main diagonal. Now for the final steps of our calculation, we apply the fundamental rule of imaginary numbers, which states that the imaginary unit squared equals negative 1. Therefore, the term negative I squared becomes a positive 1. Substituting this back into our matrix, we get 1s on the main diagonal and zeros everywhere else. This resulting matrix is exactly the identity matrix I. Physically, this proves that our original matrix perfectly preserves the geometry of the space it acts upon, confirming it is indeed a unitary matrix. Now that we have successfully verified a unitary matrix, let us look at one of its most beautiful properties. It preserves the Hermitian inner product. Conceptually, the inner product is a mathematical way to measure the angle and distance between two vectors. In this formula, x and y are our initial vectors. The angle brackets represent the inner product measurement. Ux and uy are those same vectors after being transformed by our unitary matrix. The equation guarantees that the measurement after the transformation is exactly equal to the measurement before. If the vectors grow larger, the inner product scales accordingly, but the relative geometry remains perfectly locked in place. This geometric preservation leads us to an important rule about eigenvalues. An eigenvalue tells us how much a vector is stretched or shrunk when a matrix acts on it. For a unitary matrix, the absolute value of every single eigenvalue squared is exactly 1. Let us look at the symbols. The Greek letter lambda represents the eigenvalue. The vertical bars represent its absolute value. Because the matrix acts as a rigid rotation, it cannot stretch or shrink any vector. If the absolute value were greater than 1, the vector would grow, which violates the preservation of distance. Now that we have seen this eigenvalue formula, let us understand where it comes from. We are setting out to prove that the scaling factor must be 1. We start with the foundational definition of an eigenvector. Ux equals lambda x. To find the squared length of these vectors, we take the conjugate transpose of both sides. Then we multiply these transposed versions by their original untransposed sides. This specific operation is how we measure squared length in complex mathematics. Finally, we expand the equation. On the left, we group UH and U together. On the right, the conjugate transpose of the complex number lambda becomes lambda star. Continuing our derivation, we simplify the expanded equation. On the right side, multiplying a complex number by its conjugate gives its absolute value squared, written as absolute lambda squared. On the left side, because we know U is a unitary matrix, we can replace U hatch times U with the identity matrix I. The term x hatch times x appears on both sides, representing the squared length of the vector. Because eigenvectors cannot have a length of 0, we can safely divide both sides by this length to cancel it out. This leaves us with our final result. The absolute value squared equals 1. The intuition is clear. The matrix never stretches the vector. So, we have proven that unitary matrices preserve complex lengths. This brings us to a concept that is much easier to visualize in everyday life, the involutory matrix. Think about a standard light switch in your room. If you flip it once, the room gets bright. Flip it a second time, and it goes back to dark. The second action completely undoes the first. In mathematics, an involutory matrix is exactly this, an operation that, when applied twice in a row, brings you right back to where you started. It is a matrix that is its own inverse, acting like a perfect mathematical mirror. Let us look at the mathematical form of this mirror concept. Formally, an involutory matrix satisfies a very simple equation. A squared equals I. Conceptually, this means applying the transformation 2 times in a row cancels out all changes. Looking at the symbols, A is our involutory matrix. A squared simply means the matrix A multiplied by its exact self. And I is the identity matrix, representing the do-nothing state. Because A times A equals I, it immediately means that A is equal to its own inverse. If the matrix dimensions increase, the identity matrix scales up, but the double application always returns you to the start. Before we move on, let us see this with a concrete example. We are given a matrix A that represents a geometric reflection across the x-axis, and we need to verify if it is an involutory matrix. To prove this, we simply need to multiply it by itself and check if the final result is the identity matrix. We write the matrix out twice, side by side, to prepare for standard matrix multiplication. We carefully multiply the rows of the first matrix by the columns of the second matrix, adding the corresponding elements together. We write out this arithmetic step fully to ensure we do not make any simple sign errors. Now we conclude our multiplication. We simplify the arithmetic, paying special attention to the bottom right corner, where 2 negative numbers multiply to give a positive 1. The arithmetic simplifies perfectly, leaving us with 1s on the main diagonal and 0s everywhere else. This resulting matrix is exactly the identity matrix I. Physically, this mathematical result proves that reflecting a point across the x-axis twice puts it exactly back where it started. Therefore, we have successfully verified that this reflection matrix is a true involutory matrix. Let us look at a visual representation of the example we just solved. Here we have a standard two-dimensional graph. Notice the original blue vector pointing upwards in the first quadrant. When our matrix A is applied to this blue vector, it flips it across the horizontal x-axis, creating the red vector pointing downwards. This is the first reflection. Now, follow the dashed red arrow. When the exact same matrix A is applied a second time, it flips the red vector right back to the original blue position. This perfectly visualizes why A squared equals the identity matrix. The double operation leaves the starting point completely unchanged. Now that we have seen the geometry, let us look at the eigenvalues for an involutory matrix. Remember, an eigenvalue tells us how much the matrix stretches a vector. For an involutory matrix, the eigenvalue squared must equal exactly 1. Let us break down the symbols. Lambda is our eigenvalue, representing the scaling factor. Lambda squared represents the total scaling after the transformation is applied twice. Because applying it twice does nothing, the total scaling must be 1. The only real numbers in existence that square to 1 are positive 1 and negative 1. This means the matrix either leaves a direction alone or perfectly flips it backwards. Now that we have used this eigenvalue formula, let us understand where it comes from. We want to prove why the eigenvalues can only be 1 or negative 1. We start our proof with the standard definition of an eigenvalue. Ax equals lambda x. To see what happens when we apply the transformation twice, we multiply both sides of the equation by the matrix A again. On the left side, we simplify by combining the two matrices. So A times A becomes A squared. On the right side, because lambda is just a regular number, we can safely pull it out to the front of the matrix multiplication. Concluding our derivation, we use the special property of involutory matrices. Because we know A is involutory, we replace A squared on the left side with the identity matrix I. On the right side, we look at the term Ax inside the parentheses. From our very first step, we know that Ax is equal to lambda x, so we substitute that back in. Multiplying any vector by the identity matrix just leaves it unchanged, so the left side simplifies to just x. On the right, lambda times lambda gives lambda squared. For this to be true for any non-zero vector, the scaling factor squared must equal exactly 1. We have covered a lot of ground today, so let us summarize the key takeaways. Both unitary and involutory matrices are special mathematical tools that preserve information, but they do it in entirely different ways. A unitary matrix preserves the length and angles of complex vectors, acting like a perfect, distortion-free rotation. This is the absolute backbone of quantum mechanics. On the other hand, an involutory matrix is its own inverse. It acts like a mirror that completely undoes its own operation when applied twice in a row, which is incredibly useful in cryptography. You have now mastered the foundational math behind these powerful matrices. Great job!